Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everybody. Thanks for coming. It's a pleasure for me to welcome back Richard Hartley to MSR. He's visited us a few times before. Richard actually needs very little introduction. He's a very famous professor at Australian National University. Everyone knows that he worked on projective geometry for a long time, and he has a very famous book too that's out. A lot of vision folks have it, co-authored with Andrew Zisserman. So there are some very little known facts about Richard. He likes opera. He likes to hike in dangerous places. And he actually won a prize for drinking. So at least two of those things are true. With that, Richard?
At least. Yes, okay, thanks. So, this is not all entirely my work, and really the fact that my name's first is simply because I wrote the slide. It has nothing to do with who did what. In particular, the work at the end is done largely by my student Sardeep, if we get that far. Okay, so what is a manifold anyways? So I'm going to sort of start fairly slowly giving some definitions and things so that those who are not totally familiar with this sort of thing are not lost from slide one. So this is, when I was doing research on this, I came across this thing in the National Library of Australia, James Chester Manifold, 1867 to 1918. From a family of manifolds in Australia. There were actually quite a lot of them, but they have, naturally enough, nothing whatever to do with this talk. So here are some examples of manifolds, which one would be familiar with, namely sort of two-dimensional manifolds, and we'll come back to that slide. So a manifold, didn't actually give the definition, did I? Okay, so a manifold, something which looks sort of like Euclidean space if you don't look too far. So the surface of the Earth, you may say, is a two-dimensional manifold. Every region around it looks like a region of the plane. And we're not talking about geometric with measurements, we're just talking about rubber sheet. But, well, for the time being. So, examples of manifolds, there are a lot of them, and some of them have not a lot to do with computer vision, but others do. So Rn is naturally a manifold, it's an n-dimensional manifold, because around every point there's a little bit which looks like a little bit of Rn, naturally enough. So the sphere Sn is one which, common manifold, well, like the surface of the Earth, S2. Rotation space, that's one which I've given a bunch of thought to recently and looked at in some detail. Very simple manifold, of course, but there's a lot to learn about manifolds from looking at SO3. SO3 is rotation space, three-dimensional rotations, space of three-dimensional rotation, which it's a three-dimensional manifold that you can think about in lots of different ways. Positive definite matrices form a manifold, and I'll have a bunch to say about positive definite matrices. In fact, they form a cone, as is sort of well known from those who do convex optimization. They form a cone in, if we have an n by n matrix, then that sits in Rn by n, so Rn squared, and a neighborhood there of matrices is like a neighborhood of Rn. Grassman manifolds are an interesting one. I'll say something about them later. The essential manifold sort of harks back to what I spent a lot of time thinking about in previous years. It's related to structure and motion and represents the rotation and translation of one camera with respect to another. So the set of all such possible rotations and translations is the essential manifold. And one which I've sort of looked at a little bit recently, shape manifolds, which is a sort of interesting thing. So yeah. Okay, that's manifolds. I'll say a little bit more about Riemannian manifolds in a bit. But the other main topic of this talk is about inner products, Hilbert spaces. Of course, they're tied up with kernels, which is the other thing on the title of the talk. So what is a Hilbert space? So a Hilbert space is simply a vector space with an inner product. All right. For me, it's a Hilbert space with an inner product. So dot product. Well, it does have one other property to really make it a Hilbert space. It has to be complete under convergence of sequences, but that's not really very interesting or very important to me at this point. So it's interesting, but not important. So usually you talk of Hilbert space, you think of it as being infinite dimensional, but that's not necessarily the case. So infinite dimensional spaces, things like spaces of functions on the real line or on an interval of the real line. One of the things which a Hilbert space has, which I'll talk about a little bit, is a norm, right? So a norm is basically a length. So you take sum of xi squared, gives you the length, well, it gives you the square of the length of a vector. Sorry. You can get it from the inner product, x. So if you've got an inner product, you've always got a norm. The opposite does not, of course, hold. There are norms which don't give you inner products, such as things like L1 norms. They do not arise from an inner product. So norms allow you to measure distances. Inner products allow you to measure angles, right? And distances. So an angle, of course, you get by that well-known formula. The inner product gives you the cosine of the angle, effectively. Okay, so we'll talk a little bit more about Hilbert spaces in a bit. Riemannian manifolds. So, okay, I said what a manifold is. What is a Riemannian manifold? Well, really the only thing important to me, particularly here about a Riemannian manifold, is that you can actually measure lengths of curves on the manifold, right? So here's a curve on the manifold. You can, in fact, measure its length. Gamma t is a curve. You can measure its length. Really, to be precise, it's to do with inner products on the tangent space. Okay, I didn't say that. The way I think of manifolds, I'm taking a very intuitivist view of manifolds. For me, I'm thinking of manifolds as being embedded in some sort of Rn, like a surface in Rn, right? For a mathematician, that's not entirely satisfactory. But for me, a manifold is, think of like a surface in Rn. The tangent plane is, in fact, the tangent plane, where, in the natural way, where, plane that meets at one point tangentially. So one of the things you can do on a manifold is think of a direction in the tangent plane. Think of a tangential direction. And now head along this tangent plane, head along the surface in that direction a certain distance. And the way I like to think of that is in terms of riding a motorbike on a road which is very slippery. If you want to ride a motorbike and not come off, you should arrange it so that your acceleration is always perpendicular to the surface. Otherwise, you'll slip sideways and fall. So a geodesic is a curve, which is what I'm describing here, is a curve whose normal is always perpendicular to the surface. So that's a geodesic. Geodesic can also be described as the shortest path between 2 points. So if you take 2 points on a manifold and take an elastic band and pull, it'll settle down on a geodesic, the shortest path, or at least locally shortest path, in the way I'll describe. So that's what a geodesic is. A taut piece of elastic band, curve on a surface whose acceleration is always normal to the surface. And always also a local distance minimizing curve. You can break up the curve into little sections so that it is the shortest path from gamma AI to BI. Okay? Or so maybe...
Because you're talking about acceleration, so you have to assume that manifolds are like C2 continuous or something?
Yes. I shouldn't use the word smooth here. I'm talking about smooth curves, smooth surfaces, in fact. And there is a hierarchy. What I first described as a manifold, it was a topological manifold. Next sort of level of hierarchy is what you call a smooth manifold. So on topological manifold, you can define continuous functions. On a differential manifold, you can describe differentiable functions. And on Riemannian manifold, you can describe depth and angles and things like that. So it is, in fact, differentiable and smooth in my way of thinking. Okay, so here's an example, for instance, of a geodesic. And although this red line is a geodesic, it's obviously not the shortest path from there to there, but locally it's the shortest path. It's made up of a whole bunch of little shortest paths. And that is the geodesic, a great circle. Here are examples of geodesics on various manifolds. So on a simple thing like a torus, the geodesics are remarkably complicated, in fact. On a pretzel, even more. But on things like cones, they're actually quite easy. You draw a paint line on the ground and roll the cone over it. The paint will transfer to the cone in a geodesic, on a geodesic line on the curve. That happens to be examples of them, you see. So getting back to this thing here, there's a thing which I'm going to talk about called the exponential map, which means that if you start here with velocity v heading in such a direction, and you go along the geodesic for time 1 at velocity v, you'll get to a point on the manifold, on the surface, and that is known as the exponential of v. Don't ask me why it's called exponential. It has something to do with the way these work with matrix spaces. But it's the exponential. It's a mapping from the tangent space at a point to the surface, to the manifold. And the mapping which goes the other way is called, naturally enough, the logarithm map. So a lot of algorithms, which I'll talk about that when I get to it. Geodesics and the exponential map, I've said that. So that allows you to do convex optimization on manifolds. So I've looked at that a bit in recent, particularly convex optimization on SO3 I've looked a bit recently, because of the structure of manifolds, you can start doing things which mimic convex optimization and optimization theory on a manifold. So convex sets are defined in terms of geodesics. So a geodesic is sort of like a straight line. It's your replacement for a straight line in a manifold theory, and the path between 2 points. If the geodesic between 2 points, the shortest geodesic lies inside a set, it's called a convex set, and functions are convex if they're convex when restricted to the geodesic. So you can do a whole bunch of things on convex optimization. You can also do things like define whether a function is, you can define a Hessian. The Hessian is defined like this. If you have your manifold, and supposing we have a function from the manifold to real numbers, I can define the Hessian of that function by starting out from the tangent space and mapping by the exponential map and then the function. And if that map all the way across there, which is now a map from Rn, or a Euclidean space, to R, has a Hessian. And if that is positive definite, the function is convex. So it allows you to do all sorts of convex optimization. Convex is the positive definite. So this allows you to do iteration algorithms on a manifold. There's also gradient was defined there. The gradient of this function is also just the gradient of that mapping. Same thing. And so you can define things like gradient descent algorithms on manifolds and Newton algorithms on manifolds using the Hessian. But that's not really what I want to talk about. So, but before I get off the idea of optimization on manifolds, I think I talked about this one here before, maybe about the Weisfeld algorithm on a manifold, where the Weisfeld algorithm, given a bunch of points on a manifold, tries to find the point which is their median, in the sense that it minimizes the sum of distances to the points. And your standard sort of algorithm for doing these sort of things, or optimization in general, you knew how to do optimization on the tangent space, because it's Euclidean space, it's flat, right? Is to start at a point, map up to the tangent space, do a step of optimization, and map back down again by the exponential map. Then take another tangent space and keep going. And so an interesting area of study is, when are these algorithms convergent? What is the radius of convergence and things like that? So we're looking at that sort of problem on SO3.
So the P and X are supposed to be the same, or are they different?
Yes, they are. Yes, just two different diagrams, I guess, I've been shown different places on the internet. Yeah. So, example of this is rotation averaging, where you can do rotation averaging on SO3. This is SO3 being a set of rotations. So this comes back to sort of structure and motion, where you've got a camera moving around, and you can work out what the relative motion of the cameras are. R1, also R2 to R3. Methods based on fundamental matrix or essential matrix. You can work out R2, R1. You can work out all the pairwise things. But for consistency, because rotations form a group, you need this relation to hold. So the question is, find the absolute rotations of each of the points. It's an example of averaging on a manifold, in this particular case, the manifold of rotations. So this, I think, I've shown here before, though maybe you don't remember it if you were here, even at my talk. But we did this with the Notre Dame data set, where these are all different positions of cameras, images of that, 569 images, 280,000 points, and 42,000 pairs of images that overlap by more than 30 points. So if they've got that much overlap, you can work out relative rotation between these. But some of them you can't, they don't see anything. So you get a sort of a graph like that, where these are cameras, and you can work out the relative rotation from one to the other of the camera. And then the task is to work out all the rotations, and I won't go into the details of the algorithm, but it's an averaging process where iteratively we average the rotation of one based on the supposed now known positions of all its neighbors and the relative rotations. So,
but you can also encode the confidence of estimating pairwise rotations, right? Because depending on your reliability of the correspondences, it may not be reliable. So
that's true.
Encode that.
That's true. When we were doing this, we didn't actually do that. Instead, we did the algorithm. I said the Weisfeld algorithm does an L1 optimization. So L1 is basically robust rather than L2. So bad measurements sort of not so important. And once you've actually done it, you can work out, in fact, if there are some measurements that you got that are bad, because you can sort of look around a loop, and if the loop doesn't add up to 360 degrees, roughly speaking, one of the estimates around there is wrong. And so there are processes that you could think of for weeding out bad ones.
What do you mean by average?
When I say average, I meant add up. If it were planar, which it's not, of course, then you go around a loop, rotation from there to there, followed by the rotation from there to there, and there to there, and there to there. It's got to be one complete turn, right? And if all those relative rotations don't add up to a complete 360 degree turn.
There's a co-cycle condition on those.
Yeah.
But what do you mean by the average?
Average. Okay, well, sorry, yes. Well, you can think of it as being, well, going back to this diagram, perhaps this diagram, think of this as being SO3, and you've got a bunch of rotations represented by points on this. I'm trying to mimic, it is in fact the point that is closest to all of them in some sense. Well, in fact, whose sum of distances to all of them is minimized. These would all be estimates. Suppose you had a bunch of points around here. They're all supposed to be estimates of that one, right? So, what is the best estimate of that one? It's you get it, in Rn, you would add up all the estimates and divide by n, right?
So there should be a point that within that set that the geodesic distance between it and all the others
is minimized.
Well, couldn't you find
the sum of ones is minimized? No, you couldn't assume they're all going to be equal. That'd be, in a triangle, maybe. In a triangle, yes, but if you've got n points in Rn...
Geodesic distance is not
Sorry?
their geodesic distance is not Euclidean distance, right?
But even
no, but in Rn
you
it's...
have like 5 points in arbitrary configuration and make the center point be equidistant to all of them.
Yes. So you try and get the one that's minimally distant, sum of distances is minimum. Sum of squares would be the sort of mean. Sum of distances, not their squares, is I call median. Okay?
For
Yes.
So the Weisfeld algorithm is basically iterative.
The Weisfeld algorithm is iterative. You start at a point, do an update down here, and then go back and throw that process I. And the details of exactly what you do in the tangent space, there's a formula for it, the Weisfeld formula, which explicitly, it's an explicit update formula for a gradient descent algorithm, and we can prove that it's convergent. You can prove it's convergent in Rn. You can prove it's convergent on SO3, and in fact even prove it's convergent on a Riemannian manifold with positive curvature, which I haven't really defined, but you know,
But
certainly the sphere is one.
Have to hold locally? Like,
Sorry?
So doesn't this only have to hold locally in some sense? Because on the sphere, there's sort of this antipodes of the sphere, right? Where, so isn't this only true like if you were in the upper hemisphere of the sphere?
Yes, you have to assume that things are not too randomly
Far away.
expressed everywhere. Okay. Right. Okay. So I want to finish with that and talk about well, that was a little bit more about kernels on manifolds, which I'd sort of advertised I was going to talk about. So what is a kernel anyway? I mean, so if you do machine learning, you're always talking about kernels, right? You're talking about kernels for kernel SVM, kernel Fisher discriminant analysis, kernel this, that, and the other, PCA, things like that, and I'll show these a little bit. But what is a kernel exactly from a mathematical point of view? Well, it's not exactly, but it's like a similarity measure, right? It's defined for points in some set S, any set, and K, the kernel is large when they're similar, and small when they're dissimilar. So think of it as being like an inner product. If you've got two inner products, two vectors, if they're close together, their inner product is large. If they're way apart, their inner product is 0, right, and small. So it's a similarity measure. It's analogous to the inner product. In fact, if a symmetric kernel is positive definite, then it is essentially an inner product, and I'll say what this means. So the point is that you like symmetric kernels. You like symmetric kernels because then it can work like an inner product, and then the kernel trick allows you to do a whole bunch of algorithms that use kernels, kernel SVM, and et cetera, et cetera. So the point is, which are, you know, things like SVM you use for discriminating two different classes and things like that. Okay, I'll give examples. But the point of the talk then is, when can you find these kernels, which are sort of distance measurements, or you know, between points, or similarity measurements between points on a manifold? Okay, when can you do that? So, okay, I mentioned positive definite. It's the definition of that is that if you form a matrix KXIXJ as being, you know, a matrix made up of those elements, then this really means well, this is the formula. It really means that C transpose, or C transpose KC is greater than or equal to 0. It's a positive definite matrix. So if you form KXIXJ, it's positive definite matrix. That's what the thing is, and if it's that's what the definition is for all choices of points in the set S. That has to be positive definite as a matrix indexed by I and J. And the importance is that if a symmetric kernel is positive definite, then this is just like an inner product, in that there exists a mapping phi from the set X. I was calling it S before, now I'm calling it X. Mapped from X to a Hilbert space such that K of X and Y is simply the inner product in the Hilbert space. Okay? That's what the thing is. And if you're familiar with the kernel trick, you're looking for algorithms that only really rely on inner products. And so you can do all these sort of things. So,
sorry, is the phi, is it constructive? Can you, for any k, you can produce the phi, or there's just an existence?
yes, you can. You can define a Hilbert space. You can define H, and you can define exactly what phi is. This is Mercer's theorem, basically. Yes, there is a way of doing it, but normally you don't have to worry about that. And in fact, in the case they're looking at, you seldom have to worry about constructing it, because all you're really interested about is the inner product, and that's given by K, right? So as long as you have K, you're okay. So one of the ones which one commonly uses is the radial basis function kernels, okay? So like this, kernel xy is e to the minus x squared, x minus y squared on sigma squared. I'm thinking here of when you're in a Euclidean space, okay? When you're in Rn. So x minus y is sort of like distance. So e to the minus distance squared on sigma squared is the radial basis function kernel, and that is always positive definite for all sigma, right? Where this is, in fact, is a norm in a Hilbert space. It's always positive definite, but in particular in Euclidean space. So that got me thinking, okay, why? Right? Why is this positive definite? Why are we able to use this to do algorithms with kernels? So started looking around a bit. And so the first thing you think of is, well, maybe it's just because d is a distance, right? It's a metric, so it satisfies the triangle inequality. Maybe that's it, right? Turns out that's not the case. No, so if you have a metric space d, x, y defined on a set S, which is a metric space, which means that there is a distance which satisfies the inner product, then the answer is, well, I won't say the answer yet. I'll leave it a surprise. So this being a distance is not enough. So that means, for instance, really, the first thing to think of is having a norm good enough? If you're on a vector space with a norm, will that work, right? And the answer is, once again, it won't. You actually need the product of there being an inner product. So the theorem says this: the radial basis function is positive definite for all sigma. This is the radial basis of k, x, y, defined by that, where this is a given distance. This is a positive definite kernel for all sigma if, and only if, S can be isometrically embedded in a Hilbert space. This is saying something rather different from the previous thing, where here we're taking a norm in a Hilbert space, whereas the previous thing, right, we were taking inner products in Hilbert space. It's not the same theorem. But so this is, so it's not enough for there to be a Banach space, technically. It has to be embedded in a Hilbert space, even though we're only using the norm. If there is a Hilbert space and an embedding of S into the Hilbert space, then you have a kernel. So let's have a look at some examples here. If you take a sphere that's supposed to represent a sphere, maybe it's a circle, whatever it is, okay? So there are ways of defining the distance between 2 points, x and y here. You can define the distance around the curve, right? Or you can count the distance across, the chordal distance. Well, the chordal distance on the sphere is clearly a distance which is embedded in Hilbert space. The sphere itself sits inside a Euclidean space, which is by definition a Hilbert space. It has an inner product. It's a vector space with an inner product. And the distance, if I define it as that chordal distance, is exactly the distance in the Euclidean space. Whereas there's no way of embedding that so that the distance, the Euclidean distance, is equal to the distance around the curve. So that means that if I take the chordal distance, dxy equal to sigma theta on 2, where theta is the angle, that leads to a kernel in all cases. But the geodesic arc does not give you a kernel. Okay? So we're not so interested in spheres, but we are interested in positive definite matrices for reasons that they come up in computer vision. And they come up in a number of ways in computer vision, but one of the most obvious ways, well, I don't know, maybe it's not obvious, but one of the most common ways perhaps in recognition that they come up in computer vision is through so-called covariance features, where you look at a window and you sort of take little sub-windows and you work out things like intensity across that window, and you work out gradient across that window and various other things, and you work out how they correlate. How does gradient correlate with intensity across this window? How does gradient correspond with curvature of things? These were features which were invented by Fatih Porikli and Tuzal, I believe, and they can be used because they're covariance matrices. They're how these things correlate. They are positive definite matrices, and they are used as features to describe objects. I'll push ahead a few bit. things here. This is the in-rear data set. You're trying to detect pedestrians. So what you do is you train this, right? You put a little box around pedestrians, and you take little windows and take these covariance features. So, and then you train your classifier on these, and then you run a window over it and see which windows you find contain a pedestrian or not. And so the window is described by these covariance matrices, by a little covariance matrix. Okay, so the question is, I've got a bunch of windows which have these descriptors, which are pedestrians, and a bunch which aren't. I want to distinguish between them with a support vector machine, for instance. But the covariance matrices sit naturally on this Riemannian manifold. So what we have to do is find a kernel on this Riemannian manifold of positive definite matrices so we can apply a support vector machine, and then we can distinguish between the different things. Now, about positive definite matrices, there are lots of ways that you can define distances between two positive definite matrices. Okay, so one of the useful features that you might like is affine invariance, which means the distance between x and y is the distance between A transpose x, like that. If x is positive definite, so is A transpose xa. And if this were true, then it means that every point in the space of homogeneous of positive definite matrices is sort of like any other point from the terms of it, in terms of its neighborhood, and it's a homogeneous. The thing can be gives a homogeneity condition on positive definite matrices, which turns out to be good. And you can define an affine invariant Riemannian metric using this. So a distance function on positive definite matrices. There are other metrics. There's logarithm metric. Distance between x and y is log x minus log y, Frobenius norm. It's a useful one. One called the Stein metric, where given by a rather more complex formula, these are various different metrics that one can define to look at positive definite matrices. So this is a distance, and the question is, under what circumstances does this allow you to define a radial basis function kernel? That's the question. You want a distance function which allows you to define a kernel so that you can then discriminate classes. And it turns out, if you look at various ones, which we looked at, and there are a few others as well, there's just one, the log Euclidean, which is both a geodesic distance, and what that means is it's really measuring distance along some curve in the manifold. You're not sort of going out of the space. You're not, if you have a space that curves around, it's no use measuring the distance across there, the shortcut. You have to measure the distance around through the space of what you're really interested in. So the log Euclidean is geodesic distance, and it is a positive definite kernel. And you get that it's positive definite by applying this theorem, which we had here, right? It's a kernel because it can be embedded in a Hilbert space. So this theorem allows you to sort of look at various distances and say, quickly rule out, yes, no, this is not going to work to give you kernels because I can't find, it's not going to be embeddable, or it's not obvious that it's embeddable in a Hilbert space, whereas otherwise some it is obvious. You can embed it and you can apply the theory. Sometimes it's not quite so obvious, but you can nevertheless find ways in which you can define kernels. So the log Euclidean one looks good. We applied it to various things. I'll skip over that, but one of them is the in-rear data set, and low is good here. This is false positives versus miss rate. It works. This is using a technique called multi-kernel learning, but still your kernel, you're discriminating between covariance matrices, which are descriptors of windows in the space, okay? Multi-kernel because you're actually taking several sub-windows. You're taking good sub-windows, which you can find what ones are good by training, and adding the kernels, taking linear combinations, positive linear combinations of kernels. So this is the best one we could get. And this is the kernel method based on positive definite matrices. There's a thing called the Euclidean kernel, which means you don't take the logarithm. It's it's just actually the Frobenius distance given by the Frobenius distance between two matrices. Doesn't work so well at all, and otherwise it works well. So okay, the technique works well on support vector machines. The same kernel you can use, the same kernel you can use on object classification, where you're doing kernel k-means to kernel k-means to group things which are the same among this data set. You had a question, I think?
So multiple kernel learning.
Yes.
You learn the coefficient, or you just.
Yes. You learn the coefficient.
So in multiple kernel learning and Euclidean kernel, what's the difference between those kernels?
Okay.
So you basically have different kernel level.
Yeah. Well. Okay. We are using the kernel based on the log Euclidean distance, right? We're using the kernel based on log Euclidean distance always, but the different kernels that you're adding are kernels determined by little sub-windows. So it's a combination of little sub-windows. The same kernel, yes. Yes, same kernel, but placed on a different window, and you're using them all to recognize them. So other things like, this is kernel SVM, this is texture recognition. Another one here is diffusion tensor imaging, where you're actually, so in diffusion tensor imaging, MRI imaging technique, I don't know if you're familiar with it. I'm not too familiar with it myself, but instead of just having a color at each point, you actually have a 3x3 matrix. A diffusion, sort of describes diffusion directions of fluid in the brain. And each point is sort of think of as being a little ellipsoidal cigar. And you're actually doing classification based on the 3x3 matrix there. Now, this is what there's no ground truth here, so I haven't got a lot of basis for saying that's the best result, but it looks sort of okay. Motion segmentation once again. Okay. Kernel dictionary learning on manifolds. I'm going to skip over this one fairly quickly, but it's another example where we're talking now about a different type of manifold, not positive definite matrices, Grassman manifolds. So here's the idea behind dictionary learning. So some of this work was done earlier by René Vidal. We're applying it to Grassman manifolds here. But the point is, in dictionary learning, you have some object X that you want to describe in terms of some dictionary D, okay? As a linear combination, close as possible to a linear combination of some set of dictionary elements. But you want to do it in a sparse way, so you add this L1 sum of the coefficients, okay? And you want to choose your dictionary, which are set of features or whatever they are, so that you minimize this over the choice of all possible dictionary and coefficients. So what dictionary best describes my elements here, my X? Now, how do you do this if the thing lies on a manifold, if everything lies on a manifold here? It doesn't make sense on a manifold. You can't add points on a manifold, right? It doesn't make sense to multiply V and point on a manifold by V. If you multiply a rotation by a constant, you get something which is not a rotation matrix, right? You multiply a fundamental, well, you multiply, it just doesn't, you don't have multiplication. So how do you make sense of that? So one of the ways you can make sense of it is to kernelize the whole thing, where you find a kernel phi which maps everything, maps my manifold into a Hilbert space, and then I can define kernels on that. And the question is, well, not so much the question, the idea is that now when you've mapped phi into a manifold, all the theory of kernels works as well. Sorry, when you've mapped into a Hilbert space, okay, I'll say again, because I probably got it wrong. Phi is now a mapping from my manifold into a Hilbert space. And in a Hilbert space, you can add, you can take linear combinations, and the whole thing makes sense, right? So we apply that to dictionary learning. The whole process, there's an easy way of mapping positive Grassman manifolds into into a Hilbert space, which, Grassman manifolds. I'm not going to say anything more about Grassman manifolds because I want to hop on to the last thing, which is to do with shape spaces, which I find rather more interesting. Maybe because it's the thing I'm looking at most recently. Okay, shape manifolds. Maybe you should call them shape spaces. They're not always manifolds, but they are in dimension 2. It's what captures an invariant of a set of points in Rn. So let's have a look at something like this. You have a set of points which you found in a person's face, okay? Maybe they're equally spaced points around the contour or equally spaced points around the contour. Now, you want to capture what there is about the shape of these points, right? And so you can say these are a similar shape or these are not a similar shape. So what is shape? First question. Shape is clearly something which if you rotate, you don't change, right? I don't change the shape of my head by rotating it. I don't change it by translation either. And the point that in my interpretation here, I also don't change it by shrinking. So this is what you would probably agree is what shape does. It's not changed by rotation, it's not changed by translation, not changed by shrinking or scaling. This is an idea which goes back to Kendall in a paper from 1984. And it turns out that if you define shape as an equivalence class of points under transformations of those 3 types, you call that a shape, the equivalence class. This forms a manifold. So, which is rather surprising, I find. But just let's work out how this works out. You represent each point as a complex number. Supposing we've got points in the plane. You represent points as a complex number, okay? That gives you a real and imaginary part of your 2 axes. So n points form a vector of complex numbers, okay? A vector of complex numbers is the first approximation to what you might call the shape, or something. It's the pre-shape manifold equal to the set of all complex n vectors, or m in this place. Now, if you center them so that you subtract, you've got a bunch of these things. Sorry, not a bunch of these things. You take the mean, the centroid of all these complex numbers, their mean, and subtract it out, then you've got a centered vector here. Okay? So you do that. Translation, you center it at the origin. So it's now translation is taken away. And you scale it so it has length 1. So let's get rid of the scale, right? Now what about the rotation? That's the important one. What about rotation? Now, the interesting observation here is, important observation, if you multiply this whole thing, which is a vector of complex numbers, by a complex number e to the I theta, it rotates each complex number. So it preserves the shape. So what you can think of as your shape manifold is sets of points on the complex sphere. They're centered of length 1, right? Because I've scaled length 1. These are points on the complex sphere, and I take the action of rotation, multiplying, just multiplication by z. Now, this gives you what's known as the complex projective space. To understand this, just think of, if you're more familiar with real projective space you can think of as points on the sphere with -1 and +1 identified, right? So all real numbers of length 1, -1 and +1. If you do the same thing in complex, you take points on the complex sphere and you identify them when they are equal up to a complex scale. Okay? So this is complex projective space, which is a manifold.
But it looks like it's just basically scale similarity.
Well, there's the rotation similarity as well. That's the point. Scale is fine, but rotation, it's scale. It's scale in terms of complex scale, but in terms of think of these as points on the plane, you're actually rotating, right? Which is, it's a rotation rather than a shrinking of scale, right? So it turns out that this has to do with a thing called the Hopf vibration, which I studied a little bit in graduate school in topology, a very complex looking thing like this. These are what happens if you take a point and multiply by a complex number of a unit complex number. They're circles. So in other words, if I take this and multiply by all complex numbers, it traces out a circle, right? So the complex space is made up of a bunch of circles. And it's this thing, Hopf vibration for what that's worth. But I'm getting towards the end now, so which is good. But the point of this research is, this work that I'm talking about by my student, is that he can define a kernel on this two-dimensional shape manifold, so which is shown here. Think of, as I said, a shape as being a unit vector. Well, say, forget about the fact that we're identifying the z and the z minus. Think of it as being, you forget that, because that's the way you think of these things in terms of real projective space. So just for intuition, a shape is a vector. Well, so it's an equivalence class of vectors on the unit sphere. And if we take two of them, and I want to work out what is the distance between them, right, as shapes. Well, it turns out there's this thing called the full Procrustes distance. The full Procrustes distance between two shapes now, and that is I can't reach that far, the perpendicular from one to the other one. Now, that's a good, let me convince you that is a good thing to think of as being the distance between these two shapes. The distance between the arrowheads is maybe fine as well, but maybe not quite so good as this one, because this is the smallest distance between, say, the left-hand arrowhead and any scaled version of the right? So between one shape and any scaled version of the other one, that is the minimum distance, right? And it turns out, by a bit of calculation, this in fact gives you a thing which satisfies that theorem about kernels. It turns out that this gives you the radial basis function kernel based on that distance measure on shape space, gives you a positive definite kernel, and hence you can do all the sorts of things that you like to do with kernels.
The top inner product between x and y
Yes.
are elements or n vectors in complex space.
Yes,
right?
unit vectors.
They're unit,
Yes.
the norm. But how do you define the inner product between two complex n vectors?
Okay. It's if they're AI, it's AI times BI is the normal inner product. In this particular case, it's AI complex conjugate times BI.
Okay,
Sum
so you
over I.
have to put the
Have
conjugate
to put
in
a
there.
complex conjugate, yes.
Okay.
So the point is that an inner product in complex numbers, in complex vector spaces or complex Hilbert spaces, can give you a complex number. It can give you a complex number. So you cannot just say that cos theta is equal to the inner product, because what doesn't make sense, that the cosine is imaginary. But it turns out you can define cos theta to be equal to that, the absolute value.
Complex number multiplication, and then you just take the magnitude or whatever you want to call that operation.
Yes, and that gives you cos theta, and sine theta, which is that, because the full Procrustes distance yields a positive definite kernel. Right? Various other ones do not. Geodesic distance does not. And this one, which is actually the distance between the arrowheads, does not. Right? Which is curious, because it does if you're in a real space, but not in the complex space. Okay? So, okay, that gives you a kernel that you can now look at and try and do things like classifying shapes. Yes?
So how do you find the inner product when the shapes have different numbers of points?
Well, you don't allow that. You say, okay, this is one of, there are a few weaknesses behind this in a practical sense, which I can just point out in a little bit, but yes. But it allows, and two-dimensional shapes are of somewhat limited interest, really, in computer vision. But one hopes to be able to go to three-dimensional shapes. And I've been talking, in fact, with Katsu Ikiuchi, who's here yesterday, saying, can we try to use it to classify different faces which there are on the temples of Angkor Wat or whatever it is he's So, which he says there are classes. So can we use this? So that's the work that I'm interested in doing. But for the present, we can do it for two-dimensional things now, and leaf database and things like these. So what are the weaknesses? The weaknesses are, for one thing, yes, you need the same number of points, right? And furthermore, you need them to be the correspondence between them to be made and to make sense, right? So one can think of, situations where that's possible, like you take your nose, your two eyes, your corners of your mouth, and your chin, and your ears, or something like that in an image, right? But, or obviously in I don't know, well maybe not obvious. You can maybe find the stem of the leaf, and then take a fixed number of points around the stem, around the contour of the leaf, equally spaced, right? So that will give you the same number of points and the correspondence that you can make to use to classify those. There are obviously other situations where this is going to be a problem, right? One also there's some hope of generalizing this work to things where you don't have a finite number of points, but you have a curve, and you're trying to work out shapes of curves. And I think I haven't followed this up yet completely, but people do talk of shape manifolds in that sort of sense too, where it's not a finite number of points. But at the present time, I'm not sure of the details. To get this into 3D, there are problems too, which means that we haven't just immediately gone and done it. In that, in 2D, this 2D space, I said it's a complex projective space. It is in fact a manifold. In 3 dimensions, this is not a manifold. It's normally called shape space, not a shape manifold. It's sort of like a manifold with cusps and things. So I don't know quite how to handle that at this point. But one does research and hopes to find answers to some of these problems. So, okay, that's it with the various people who I worked with. This is a different list of people, not exactly the same list as before, but the union of the two lists is the union of collaborators on this work. Okay, that's it.
Trying to understand when you say something like this is not a shape space, this is a shape manifold.
Yes.
What exactly do you mean? Because there's always some space in which the manifold is embedded, and you can always think of that as your shape space. It's like taking a set and relaxing it into a larger set. And it seems that a lot of computer vision people take their features and turn them into vectors, do all the work with vectors, and then maybe at the end they project back to the manifold. Okay, maybe I don't know really about the last part, but what's wrong in working in that vector space?
Well, there are a number of things wrong with working in the vector space, I guess. It depends on the particular application you're looking for. If you're talking about kernels in particular, I'll sort of sidestep that for the moment. But if you're talking about averaging, for instance, finding on clustering, if you're doing things like clustering on a manifold, there's no point finding the center of a cluster in the space, in the embedded space, because it does not represent an element that you're looking at. And if you think of very specific manifolds like rotation space, the sum of rotations is not a rotation, right? The Grassman manifolds, it's not. So the way Grassman manifolds, I skipped over it, is you're applying Grassman manifolds to represent sets of images. Well, if you do clustering with Grassman manifolds and try and work out, where the center, the most average sort of, thing is, it's not going to be a member of the Grassman manifold. It's not going to correspond to a plane. It just won't be right. Distance is also, as I said, if the manifold, in inverted commas, sort of comes around and like this, you really want to find distances around the hole through the space of possible configurations, not across the gap, which is really just something to do with the particular way that's embedded, right, in our end. For a different embedding, it might be completely different, but the intrinsic thing is in the manifold itself, and so that's why you want to deal with the manifold. But the experiments also support this. Right? It'd be best to be doing these things with intrinsic metrics, intrinsic distances on the manifold. Okay?
Any other questions? Actually, I just have one. So when you talk about comparing shapes, does it allow you to compare against different categories of shapes? I mean, show the leaf, so you're saying, okay, can I distinguish between, maple against others? And even the maple leaves don't look exactly the same.
Yeah, well, I mean, it depends on the granularity of your clustering, I guess, right? So we are talking about there, and he's done the experiments where, in fact, you are taking maple leaves and comparing them with beech leaves or something like that. But if you bothered to train your classifier on maple leaves when they're young and in spring or something like that, and what they look like, I'm sure you'd find that you'd be able to find differences in shape as well. And as Katsu was saying to me yesterday, they weren't using this technique, but they did, for instance, find in which I think was very interesting, in these faces in Angkor Wat, that there were differences between clusters of these faces. They all looked like people's faces, but the clustering was perhaps based on having different sculptors who did these things. Well, some of them supposed to represent humans and some of them supposed to represent gods, and so you can actually distinguish between them. So, sure, you can do as fine a classification as you like. Really, well, obviously, within limits.
Any other questions? Well, if not, let's thank Richard once more.